The happy recording is now in progress. We've been talking about substitutions and elimination reactions. I want to pick up with elimination reactions. And because we are in a little bit more of a hurry, because your instructor is talking about chubby cheeks on babies instead of chemistry, what I want to do is truncate our discussion of elimination reactions because so much of elimination reactions are the same as substitution reactions. So the two things I really want to focus in on are the base and the solvent, right? Because it doesn't really matter the substrate substitution pattern. If it's primary, secondary, tertiary, all of those can go either E1 or E2. There's a slight preference, but not that big of a difference. So the factor I want to talk about with eliminations that is the most important is the base. And I think I used black for the nucleophile, so use black here for base. Base is the artist formerly known as nucleophile, or let's say previously known as. But here's the deal. Nucleophiles and bases are very, very similar to each other. In fact, when I told you about nucleophiles, I said, if you are a strong base, you are often a strong nucleophile. Basicity and nucleophilicity mirror one another. So this can get a little confusing, but I got some timely advice for you, which is all strong nucleophiles are strong bases. All strong nucleophiles are strong bases, but not all strong bases are strong nucleophiles. It's not a riddle. It's helpful. That's right. We should have had that for the poem. All strong nucleophiles are strong bases. There is no section here. This is Dr. Green's own little machination of the whole chapter. So I'm kind of squishing together. This is near the, I don't even know. I've remade this chapter up. Okay, all strong nucleophiles are strong bases, but some very smart people told me if someone says but to you in a sentence, everything before the but isn't true. This is still true. All strong nucleophiles are strong bases, but not all strong bases are strong nucleophiles. The difference is size. Steric hindrance is going to determine if you're going to be more of a base or more of a nucleophile. So I like to think of it like this. If we were out hunting some big game, let's say like buffalo, right? The tastiest buffalo, the biggest buffalo is right in the middle of the herd, right? So if I'm a nucleophile, if I have too much electron density, that's the buffalo I want to go get. But to get to that buffalo, I got to get through all the other buffalo. And I don't know if you've seen a buffalo before, but they're massive, right? These are like, go out to the tall grass prairie immediately if you've not been there. Maybe not right now, it's stormy, but later on, go see buffalo. They're super cool. If I want to get into the middle of the buffalo herd, I've got to weave my way in between all the other animals in that herd. That is difficult to do because they are big. The only way I'm going to be successful in doing that is if I am small. If I have to carry an entire wagon with me and pull it through the buffalo herd to get over there, it's not happening. So what buffalo do I get to hunt? I have to pick off the sickly buffalo at the edge of the herd, right? Because if I'm big, I can't get into the middle where there's a whole bunch of crowding. I can just go to the outside and pick from the outside. That's what a base and a nucleophile are doing. Bases and nucleophiles both have too much electron density. If you are big, you can only take a proton because protons are at the outside of the molecule. You can't go in and attack a carbon to displace a leaving group because it's too much in the center of the molecule. So your steric hindrance, your bulk, prevents you from going in and acting like a nucleophile. The difference between a nucleophile and a base is size. For instance, if I had CH3O minus, that molecule is called methoxide. And let's compare that to a T-butoxide. This is methoxide. This is T-butoxide. Methoxide is both a strong base and a strong nucleophile. It is the Swiss Army knife of electron-dense things. It's small enough that it can go into the center of a molecule and make an attack at a carbon, which is the bigger, juicier buffalo, right? Because if the oxygen has a negative charge, it wants as many protons as possible to hand off its electron density to. If I'm a nucleophile and attack a carbon, I have access to 6 protons. That's great. If I'm a nucleophile and I attack a hydrogen, I have access to 1 proton. So that's not nearly the same payoff, right? This oxygen can act like a nucleophile and get into more positively charged nuclei. It is also perfectly capable of taking protons as well, both a strong base and a strong nucleophile. T-butoxide, on the other hand, is not good at doing both of those things. The O- here is not as good of a nucleophile because if it wants to go attack a substrate, it has to bring its whole family with it. This is like the person running through the airport with all the luggage. Their flight leaves in 5 minutes and they've got like everybody with them. Home Alone stuff. I guess Home Alone reference too old. Anyway, they are stressed out because they're carrying all their stuff, right? If you're backpacking through Europe, you can be 5 minutes to your flight because you have a backpack and you're quick, right? This slow molecule prevents it from acting like a nucleophile, but will still allow it to act like a base. So T-butoxide is a strong base. But a weak nucleophile. And that's really the major difference between if something's going to be a substitution or an elimination reaction. We're going to have an electron dense thing. If the electron dense thing is larger, it will act more like a base. If it's smaller, it will tend to act more like a nucleophile. Now, that's not always true, but that's generally a pretty good rule of thumb. All the other factors that we've talked about, the substrate substitution pattern, the solvent being protic or aprotic, and the leaving group are all the exact same. So as the substrate becomes less sterically hindered, it favors E2. As the solvent becomes aprotic, it favors E2. So you use your same factors that we talked about for substitution and apply them to elimination. But it's the nucleophile base that really pairs these apart from each other. Now, is it going to be fair for me to say, give you a bunch of reagents and say, is this reaction going to be a substitution or elimination? I could, but I'm going to tell you in advance that I will tell you if it's going to be a substitution or elimination. The MCAT is not as nice as I am. And so it will ask questions like this, where it's going to make you choose if it's going to be more of a substitution or elimination. Larger bases like this will almost always be elimination only. Molecules like this, it's tough because this can be both a base and a nucleophile. So I would expect a mixture of products using methoxide. So the way that I will normally ask these questions is I will give you a reaction and I will say, for the following elimination reaction or for the following substitution reaction, tell me what the mechanism is. Go through your 4 factors, right? I will let you know what it is and then have you go from there. Questions about eliminations? Okay, the other thing that we need to talk about with eliminations is the stereochemistry. So just like with SN1 and SN2 reactions, which are not labeled very well for how many products they make, the type of mechanism that an elimination follows matters because it will change up the type of product that we're going to form. All right, so I need to go back to a super fun thing that we talked about a while ago. Wait, let me use our same colors. Our substrate's typically in blue. Leaving group was in red. All right, I need to look down this molecule. Creepy dead eyeball. To draw what kind of projection? The Newman projection. Remember those guys? And we can spin molecules. We're going to spin some molecules again. So when I look at this molecule from the front, I'm going to see something that looks like this. Is the hydrogen going to be on top, left, or right in the front carbon? On top, right? Because as I look at it, hydrogen's facing up. So those are CH3s. Where's the leaving group on the back carbon? Facing straight down. And then, oops, and then there are methyl groups facing on either side of this. Staggered or eclipsed? Staggered. We are now going to call this by a different name. Staggered in this orientation means that the hydrogen and the leaving group are on opposite sides of each other. So they are on the same plane. We're going to call that periplanar. And we have a word for this when we talk about things being on opposite ends of the molecule in a Newman projection. They're called staggered what? Anti, right? Gauche is when they're next to each other like that. Another Newman projection. When they're on opposite ends, we call that anti. We need this type of orientation for an elimination reaction to take place. It is called anti-periplanar. That means opposite each other, anti. Periplanar means within the same plane. I can draw that hydrogen in that leaving group. Here's a plane. Oh, it's too high. Anyway, up there, right? So they sit within the same plane, but they're anti to each other. The opposite would be if I rotate around this and have my hydrogen and my leaving group like this. So this is a Newman projection where I've just spun around that carbon-carbon bond. If I do the same thing and look down the sigma bond here, hydrogen's still facing straight up. Where's my leaving group now? Facing straight up, not in the gauche, but now it is eclipsed. A total eclipse of the leaving group. When the leaving group moves back like this, it eclipses behind the hydrogen. This is an eclipse structure. And what we would call syn periplanar. So what that means is in the same plane, right? I can still put a piece of paper up here and show you that hydrogen and the leaving group are in the same vertical plane, but now they're on the same side of that plane. So we call that syn, S-Y-N, periplanar. This is the geometry we need to get an E2 reaction to run. It's a 2.
Easy.
Oh yeah, so because I'm differently abled with my left hand, when I put Z's, I put little dashes on them. It's a 2. All right, hold on. This could be the best 2 you've ever seen. 2. Yeah? Two. E2 reactions follow anti-periplanar geometry. Who cares? You guys care because you can predict the stereochemistry of the product. So what if we don't have a bunch of methyl groups on there? So in this one, methyl, 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 doesn't matter. What if we have different things attached to this when we're going to make our alkene? What does that look like? Let me show you. Keep it in blue. Anytime I commit to this many colors, I always regret it because I have to keep up with them. Okay, I'm gonna put a phenyl group on here. I don't think I've talked to you guys about phenyl groups. pH equals phenyl. This is an OChem 2 thing. Phenyl equals a benzene ring, which you don't know what benzene is either. It's this 6-membered ring with 3 double bonds attached to something. So don't worry about that. It's just a phenyl group. It's going to be a different marker. I'm going to put a phenyl group on here, a fluorine, a hydrogen, and another phenyl group. So I'm intentionally putting different things on either side of this because I'm going to mess with it in a second. Is this in a reactive orientation for an E2 reaction to take place? No. What kind of orientation is this? Eclipsed or syn periplanar. So no reaction can take place as is. If I want this molecule to eliminate, I need to first rotate it around that bond so that I can get, and by the way, this is not a real organic chemistry arrow, but it should be because I think it's whimsical. I need to rotate around that bond to get the bromine to go down this way. Okay, so I didn't change anything about my carbon on the left. The fluorine is still back. The phenyl group is still in front. But these guys do rotate. When the bromine went down, who's on the wedge over here? Not the hydrogen. The phenyl. All right, I'm gonna do it. It's gonna be stupid. Are you ready for the dumb? Bromine's facing up. Let's see, how can I do this? Okay. Bromine's facing up, red marker. Hydrogen is on a wedge this way, right? So the bromine has to go down. So the bromine has to go down, which means the hydrogen goes in the back. Ready? Okay. Bromine facing up. You see the stupid things I do for you guys? Hydrogen's on a wedge. As the bromine goes down, hydrogen goes to the back.
It kind of reminded me of like the turnstile.
Yeah.
type.
Yeah, absolutely. It's very much like a turnstile.
Probably should already know this, maybe it's obvious, but what is the like underlying why behind that orientation being necessary for those reactions to occur? Like,
Oh, so you
trying to,
that's a great question. So in the same way that the SN2 reactions occur via backside attack, have you watched that video? Okay, so when we talked about nucleophilic attacks being from the backside, there's a kinetic energy that's basically transferred from the nucleophile that physically hits the substrate and injects the leaving group. It's the same thing here. The base is going to hit from this side, the leaving group's going to leave on the other side. So the problem is that it's really a molecular orbital, but if you think of it from kinetics, the base is going to come in. I'll show you this mechanism in a second. Take that proton, this bond's going to break, and the bromine's going to leave. So if you look at it, the action's kind of happening this way. Right? It gets lined up along this axis running down the molecule. If it was the other way, it would take the proton and it would have to go, the electrons would flow kind of like a U. And symmetrically, that doesn't work out very well for the electrons. Okay, so if the bromine is facing up, I'm sorry, when the bromine goes down, the hydrogen then goes to a dash, which means the phenyl group goes to a wedge. Do we see that orientation change? So just like Joshua was asking earlier, the next step here is for the base to come in here and take this. And we need the orbitals of these things to line up. So there's some other pieces of this that come into it, but you can think of it in terms of the base is going to attack from this side of the molecule. So if we use something like hydroxide, which could act like a nucleophile as well, it's going to take that proton, this bond is going to form, and that leaving group is going to leave, and they're all going to happen kind of in a plane. Base comes in from this side, leaving group leaves from the other side. That is going to leave us with a alkene, right? Because I made a double bond here. So now we got to be careful about what we put on each side of this alkene. I'm going to leave when we make a decision for one part of the alkene, that sets the geometry for the rest. So I'm going to put the phenyl group here facing down. That was arbitrary. I could have had the phenyl group facing up on this side, either way. If the phenyl group is facing down, the fluorine is then going to be on the opposite side like this. Right, so when I put the phenyl group here, it forced me to put the fluorine there. I could have put the phenyl up here, fluorine down there, doesn't matter. Now that the phenyl is down here, What goes on this side? The other one. Take a look at this. When this locks this in, right, I'm not going to be able to spin this molecule anymore. So if this gets locked in as a double bond, the pieces of this molecule are going to stay on each side. If I have a phenyl group on a wedge on one side and a phenyl group on a wedge on the other side, and a double bond gets locked in here, they now get locked into the same side of that molecule. So because I have a phenyl on a wedge and a phenyl on a wedge, I put the phenyl down, the phenyl goes over here. The double bond says, no more spinning. You stay exactly as you are. No, you're right. So I have a phenyl group on a wedge on the left. I have a phenyl group on a wedge on the right. So as far as that molecule is concerned, they're both going out like this. My chest is about to receive a double bond. Now, previously, I could spin these things, right? But once I get a double bond, they're locked in, which means the phenols are on the same side of that double bond now. I arbitrarily drew this one down, which means this one has to be down, which means the hydrogen is going to be face up over here. I could have just as easily drawn, so that molecule looks exactly like this. If I would have drawn the double bond here and said, I want to put the phenyl group facing up, totally fine. That would put the fluorine facing down. What goes here? Phenyl. Hydrogen.
So both on the same side because of the phenols are on the same side because of the wedges.
They are on the same, yes. The phenols are on the same side because both the phenols are on wedges here.
For the double bond forms, wouldn't the phenols want to be away from each other?
Yes, they would. Yeah, so this is actually the most stable version of the molecule because the phenols are the biggest. And so so remember there's free rotation. So it's not like they sit totally away from each other all the time, but they are happier being away from each other. It's that no elimination reaction can occur in this orientation. I have to spin it to put it in a reactive orientation, and then the elimination can occur to make my alkene.
How does the spinning happen?
It's Newman projections. Remember, it's a sigma bond, so there's free rotation. There's energy differences, but they're not so big that it can't overcome it. Now, there's not free rotation here. Once this double bond forms, the phenyl groups are locked in together, so they're not happy about the situation right now. Questions about elimination geometry? So that's my crash course on eliminations. We need to talk about instrumentation. And I think I'm going to just drop mass spec altogether. So we can I'm less concerned with you all with mass spec and IR. I'm much more concerned with NMR. So let me bring up this one more time. I'll go through it here today, but I want you guys focused on chapter 13. That's what we're going to cover all of Friday. If you've not been reading about chapter 13, do so like now. I want you to be as read up on the NMR chapter as you can. We'll go through the basics of infrared spectroscopy. I'll talk a little bit about mass spec in here, but it's not actually used that much in organic chemistry. It's used in a lot of other fields. So what I want to do is start with this second one, infrared spectroscopy, which is down here. Something that we've not talked about in this class the entire time is how do we know what an organic molecule looks like? I draw them up on the board, right? But we don't just walk up to a flask and go, oh, that's an alcohol, right? And it's got this structure to it. We can't just smell it or look at it and figure out what the structure is. We have to use instrumentation to be able to determine this. And by the way, these slides are on Blackboard. Right? So you can pull up under the assignments tab for chapter 12 and 13. You'll see the PowerPoints on there. So don't worry about notes on here. In order to determine the structure of an organic molecule, we have three principal techniques: mass spectrometry, infrared spectroscopy, and NMR spectroscopy. By far, the most important organic technique that we use to determine structure is NMR spectroscopy. If you can give me one instrument to solve all structures, I want proton NMR. I don't need the other ones. The other ones can be helpful, but proton NMR is the most important. So that's why we're going to talk about these other ones first, because they are kind of cursory. The one I think is more important between mass spec and IR is infrared spectroscopy. Infrared light is what we call heat. we don't think of heat as an electromagnetic wavelength, but it is. We just can't see it. If you get food from a restaurant that's been sitting out for a little while, it's under a red lamp. It's not that they're trying to make the food look spooky with a red light. It's that they're irradiating the food with infrared light, and you happen to see some of the red that's coming out of it. The rest of it is heat. If you ever stick your hand under a heat lamp, it'll feel hot to you, right? More so than these lights do. Molecules also absorb light in the infrared spectrum. And when they do, the bonds start to vibrate, and we can measure those vibrations to say what kind of pieces of a molecule are present. IR spectroscopy tells us about the nature of bonds, which really tells us about functional groups. So the main takeaway here is IR spectroscopy tells you about functional groups. When a molecule absorbs energy, it has different ways that it can stretch and bend and wiggle. We call these kind of different dance moves. I like to think of them like the Carlton, which you probably know about. The molecules, when they absorb heat on a molecular level is motion, right? So we can see these types of asymmetric stretches, symmetric stretches, wags, rocking, all sorts of stuff, right? And every time you have one of these things, you can pick up on one of those signatures. There are lots and lots of tables of IR. I do not need you to memorize IR tables. I'm going to show you a few that I want you to be familiar with. But if you just search for IR stretch table or just IR table, you'll see pages and pages and pages of these things. You can look those up. I know you know how to use Google. What I want you to be able to know how to do, what I want you to know to be able to do is how to use these numbers to identify if a functional group is present in a molecule. So let's look at a couple of these to, one, figure out what an IR spectrum looks like and how to use the stretches to tell what's in there. Here are three different IR spectra of hexane, hexene, and hexyne. So this is one hexene, one hexyne. So they look like this top one is just 1, 2, 3, 4, 5, 6 carbons. This one is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 carbons with a double bond present. This one is 6 carbons, 1, 2, 3, 4, 5, the triple bond present, 6. I want to highlight the fact that each one of these has CH bonds bound to a carbon that is either sp3 hybridized, sp2 hybridized, or sp hybridized. We can find those stretches, CH bond to an sp3, sp2, or sp hybridized carbon in an IR, and we can use that to help us determine what kind of functional group is present. The area that we're going to be looking for, and I think I bring this up later on, is around 3000 for this. So focus in on the 3000 area here. Notice the area of 3000 is a little bit different for each one of those. There's a big peak in each one of these, but there's no smaller peak over here. There's a little bit of a smaller peak over here, and there's quite a bit bigger, smaller peak over here. Those are the CH bonds to an sp2 or sp hybridized carbon. We'll talk about that again here in a second, but that's the signal we'll be looking for to say, oh, there's an alkyne in this molecule, or oh, there's an alkene in this molecule, or this one doesn't have one of those groups. Now, it doesn't tell us which alkyne it is. It doesn't tell us which alkene it is. So if you gave me just an IR, I would say, okay, there's probably an alkene in here. That's the only information I have. It'd be like if you were watching security footage and you see like a black car go by, but you can't tell if it's an SUV or a sedan. You just go, it looks like it has 4 wheels. The police are going to go, great. I'm looking for something with 4 wheels. Helpful. Right? NMR, on the other hand, is going to say, no, it's a black Tahoe 1987. If they made the Tahoe 87, it'll give you very specific information. Right? So we get classes from IR. We'll get specific structure from NMR. The way we're going to do that is we're going to use these tables. Go back up here. We'll use these tables to figure out where stretches show up and then identify if those peaks are in the spectrum of interest. There are general trends about where peaks show up. I don't need you to know that. The main thing I want you to focus on here is this region called the fingerprint region. Everything from 1500 below, which by the way, 2 weird things about IR spectrum. One, the big numbers start on the left. So that's weird because it's wave number. So it's this weird unit we use. So 4000 on the left, 500 on the right. The numbers get smaller as you go left to right. That's not normal. And the signals come from the top. Why we have the signals come from the top, I have no idea. Every other spectrum on the planet, signals come from the bottom, right? But in IR, you'll always see them come from the top. So it's easier to identify. This region from 1500 and below, so this area, is what we call the fingerprint region. It is really busy. And it's hard to tell what kind of molecule, what kind of functional groups are present in the fingerprint region. So we're going to ignore the fingerprint region for most molecules. I think I've mentioned before that my wife works for the Tulsa Police Department. So if I left a fingerprint up here, experts from her lab could come in here, lift that fingerprint, take an example from me, compare them and say, Nathan was up here. Something that would absolutely not happen is my wife would come up to this and go, oh, honey, what were you doing here? Right? Because she knows me really well, but she doesn't know what my fingerprint looks like. It's busy, and my fingerprint looks very, very similar to your fingerprints. So these areas can be used to say if this molecule matches an unknown, but I don't want you in the business of trying to look into these areas, right? Look at this one in particular. This is the fingerprint region for that spectrum. Look at all the freaking peaks in there. It's really hard to be able to say which one of these is what, because there's so many going on. Same thing over here. These areas are super busy, and they are troublesome to try and identify what is a peak of interest and what's just noise in the background. So out the gate, we're going to ignore half the IR spectrum. The signals we're ever only going to look for are above 1500. Okay. So learn by doing. Let's say that I was not a very good chemistry student. So this could be a real example. When I was in undergrad, I had a nasty habit of pouring liquids into beakers and not labeling them because I was in too much of a hurry. So I pour ethanol, CH3CH2OH, into a beaker. That's a clear liquid. And I pour dimethyl ether into a beaker. That's a clear liquid. And I leave them on the countertop and I go get lunch because not only am I a bad student, but I'm also hungry all the time. I come back from lunch, I see my two clear beakers and I go, oh, darn, which one is ethanol? Which one is dimethyl ether? I don't have an NMR present, so what I do is I take an NMR, or I take an IR of each one of these things. What peak on this table could I use to identify ethanol compared to dimethyl ether? Are there any stretches up here that are in one molecule but not the other? For the alcohol, right? Both of these molecules contain a CO bond. So I don't want to be looking for my CO bond, not to mention it's in the fingerprint region anyway, but a CO bond is present in both, so it's not helpful. This molecule has an OH bond. This molecule does not have an OH bond. So I could go over here to where the OH is and say, does my IR show a signal at 3400? If yes, it's an alcohol. And if I put it in there and I just need to know which one's which, I know the signal that has 3400 is my ethanol. That makes sense? Would use it? Now, what would not happen, let me go back to, this is, my wife's lab has a lot of examples here, right? If my wife's lab gets a white powder into the lab and they take a measurement of it and it's got an alcohol on it, they don't go, oh, this is cocaine, right? Lots of things have alcohols in them. Cocaine actually doesn't, but they wouldn't make a determination on that because all they get is a class of molecules. And there's lots and billions and billions of molecules that have alcohols present on them. So that's why this is not as helpful for determining unknowns. And you know what? Actually, instead of having to go through all of these, because most of you have taken lab as well, let me leave it there for now. Does that make sense? The general trend of what we're going to try and do with IR? Okay, that was insanely fast, right? So what kind of questions are fair game for me to ask of you? Basically, the only information you can take away from today's lecture on IR is IR spectroscopy is used to determine what? Functional groups. IR spectroscopy tells you about functional groups. You want to know the structure of a molecule? Read chapter 13. That's the subject of our last lecture on Friday in the morning. All right. Have a wonderful day. I will see you later.